You hear the word quantum and you think physics labs, equations, things locked away from daily life, but quantum tunneling isn't theory anymore. It's running through your phone right now. It's inside every star you see at night. It powers reactions in your own cells, particles slipping through walls they shouldn't cross, energy appearing where classical physics says it can't. Not magic, math. And that math is everywhere. 7 ways this phenomenon breaks into the world you touch, see, use. No lab coat required. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Quantum Insider, published October 7th, 2025, covering the 2025 Nobel Prize in Physics for Macroscopic. Quantum Tunneling and Proceedings of the National Academy of Sciences. December 8th, 2009, on enzyme quantum effects in nitroalkane oxidase, catalyzed proton transfer, plus research from Nature Scientific Data, February 11th, 20. 21 on computational scanning, tunneling microscope databases with 716 two-dimensional materials analyzed. Now back to the information. 14 million Kelvin in the solar core, hydrogen nuclei slamming together, 2 protons, positive charges, they repel. The Coulomb barrier sits at 25 million electron volts. The protons only carry 4 to 9 million electron volts. Classical physics says stop, no fusion, no light, no life. 1 in 10 to the 28th power for each collision, but the sun holds 10 to the 57th hydrogen atoms. Enough collisions, enough tunneling. 1 proton converts to a neutron through the weak force. A positron emits, an electron neutrino escapes. Then deuterium fuses with another proton. Helium-3 forms in 1 second. 400 years later that helium-3 fuses again. Helium-4. Energy, light. Published in Big Think, January 25, 2025, and verified in multiple astrophysics papers through 2024. The sun has burned 4.5 billion years. It converted hydrogen mass equal to Saturn into energy. E equals mc squared. Einstein's equation. Gamows tunneling, your existence. Too slow and they'd collapse. Tunneling sets the clock. The Gamow factor quantifies it. Temperature, nuclear charge, kinetic energy, all in one probability. The temperature problem stumped everyone. Gamow's 1928 paper in Göttingen changed physics. He was with Max Born, the mecca of early quantum theory. He realized radioactive decay of uranium by alpha particles might be quantum tunneling. It was known that nucleons bound together with some unknown force, an effective binding potential. But charged alpha particles feel strong electrostatic repulsion from nuclei. Gamow combined both potentials, created a landscape similar to what Lothar Nordheim studied in 1927. The exponential term in Gamow's equation depends on nuclear charge, alpha particle charge, and particle velocity. He could express decay rates accurately. Then he flipped the problem. Decay in reverse is fusion. Same tunneling mathematics. Same quantum probability. He published a series of articles on tunneling between classically allowed regions through a potential barrier. Then, Leonid Mandelstam and Mikhail Leontovich found it independently in 1928. Gamow applied it to nuclei. Ronald Gurney and Edward Condon published the same solution independently the same year. All 3 used the Schrödinger equation published in 1926. The barrier doesn't vanish. The particle's wave function leaks through. Probability on both sides. Nature doesn't ask permission. Neutrinos convert chlorine-37 to argon-37. He counted atoms. Nobel Prize 2002. Kamiokande in Japan. Water Cherenkov detector. Super Kamiokande. 50,000 tons of ultra-pure water. Sudbury Neutrino Observatory in Canada. Heavy water. Every detection matches the tunneling prediction. The neutrinos come from that first proton-proton fusion step, the one that needs tunneling to happen at all. The CNO cycle in massive stars also tunnels. Carbon, nitrogen, oxygen catalyze hydrogen fusion. Same tunneling mechanism, different path, heavier stars, hotter cores, still tunneling. Hans Bethe worked with Charles Critchfield in 1938 to enumerate the proton-proton chain. In 1939, Bethe published the CNO cycle discovery. Both require quantum tunneling. Physics doesn't care about star size. The wave function extends through the barrier either way. Robert Atkinson and Fritz Hautermans made first estimates for stellar fusion rates in 1929, based on Gamow's tunneling theory. Everything fit. Diprotons form far more often than deuterium. Almost all proton-proton collisions create temporary helium-2, 2 protons bound together, but diprotons decay immediately back to 2 protons. Unstable, no strong force binding without a neutron. Only when tunneling combines with a weak interaction does 1 proton convert to a neutron, creates stable deuterium. The weak force is slow. That's why fusion takes 9 billion years average per proton. The weak force limits it. not the tunneling. Tunneling happens constantly. Weak force conversion is the bottleneck. Named for Ralph Fowler and Lothar Nordheim, who described it in 1927. Electrons tunnel through an insulating oxide layer into a floating gate, trapped. No power needed to hold them. This was the revolution. Non-volatile memory. Power off, data stays. Now 3 nanometers in 2024 chips. The oxide layer creates a potential barrier. Height around 3.2 electron volts. Width varies by manufacturing process. Doesn't matter, tunneling works. 18 volts in the control gate in early NAND. 15 volts in modern chips. Creates a massive electric field. 8 million volts per centimeter. 10 million in denser chips. Electrons in the channel acquire energy from the field. Not enough to jump over the barrier classically, but enough to increase tunneling probability. They tunnel up through the oxide, into the floating gate. They stay there, years, decades. The oxide is too thick to leak back quickly, 1 bit stored. Erase mode. Apply voltage to the substrate instead. Opposite direction. Negative voltage on control gate, positive on substrate. Electric field reverses. Electrons tunnel back down, through the oxide, into the channel. The gate empties. Bit flips to 1. Published in the Journal of Applied Physics and detailed in semiconductor physics textbooks through 2020. The process is called Fowler-Nordheim tunneling in both directions. Same physics, different field direction. Each cell is a metal oxide semiconductor field effect transistor. MOSFET with a floating gate. Floating gate charged means high threshold voltage. Apply red voltage to control gate. Current doesn't flow, rate is 0. Floating gate empty means low threshold voltage. Apply read voltage. Current flows, read is 1. Or in modern multi-level cells, 4 charge levels, 8 levels, 16 levels, 2 bits per cell, 3 bits per cell, 4 bits per cell. All controlled by how many electrons tunnel into the gate. Triple level cell, quad level cell, storage density multiplies. Western Digital, Kioxia, formerly Toshiba memory, 128 layers in development, 176 layers demonstrated in research. Each layer uses tunneling, billions of cells per chip. Trillions of write erase cycles across a drive's life. Each cycle is tunneling, electrons moving through barriers. 10 megabytes for high resolution, stored in NAND. Quantum tunneling wrote every byte. Your laptop, SSD, 512 gigabytes, 1 terabyte, 2 terabytes. Consumer drives, 4 terabytes in 2024, 8 terabytes in enterprise. Every boot, every file save. Tunneling moved electrons through oxide barriers. No tunneling means no modern storage. Hard drives only, magnetic platters, moving parts. Slow, fragile. Tunneling probability equals EE to the negative 2 times the square root of 2 times mass, times barrier height divided by h bar squared times barrier width. Make the oxide too thick, and electrons won't tunnel during write. Takes too long. Data won't store in milliseconds. Make it too thin, and electrons leak back during storage. Data degrades in months. Engineers found the sweet spot, 3 to 10 nanometers, depending on voltage and temperature and required retention time. Data retention is 10 years typically, guaranteed specification. That's how long electrons stay trapped before enough tunnel back to flip the bit. The oxide barrier isn't perfect. There's always a tiny tunneling current. But it's measured in attoamperes, 10 to the minus 18 amps, femtoamperes, 10 to the minus 15. Takes years to discharge. Manufacturers over-engineer. 20-year retention in practice for single-level cells, less for multi-level cells. More charge levels mean less margin, but still years. The math works. Quantum mechanics is predictable. The floating gate became the most popular approach for charge storage in silicon non-volatile memory in late 1970s and early 1980s. More than 20 years after Kong and C's concept, Toshiba in 1988 applied Fowler-Nordheim tunneling to both program and erase in the NAND flash cell. Area efficient, high density. The invention changed computing. Leo Isaki won the Nobel Prize in 1973 for discovering tunneling in semiconductors. 1957, Japan, Tokyo Tsushin Kogyo, later Sony. He made a heavily doped PN junction. Doping concentration above 10 to the 19th atoms per cubic centimeter. Depletion region shrinks to 10 nanometers. Electrons tunnel through. Tunnel diode born. Negative resistance. Fast switching. Microwave oscillators. The foundation for all semiconductor tunneling devices. Recognition came fast. Impact was immediate. More on that next. NAND won the market for mass storage. USB drives, memory cards, SD cards, micro SD, compact flash obsolete now but used for decades. All NAND, all tunneling. Charge trap technology in some modern designs instead of floating gates. Silicon nitride layer instead of polysilicon gate. Still uses tunneling. Fowler-Nordheim or hot electron injection. Both are quantum mechanical electron transport through barriers, sharpened to one atom at the end, electrochemically etched in sodium hydroxide solution. The very last atom on the tip does the imaging. Position it 1 nanometer above a conducting surface, less than 10 angstroms. Apply a voltage. Millivolts to volts depending on the sample. Electrons tunnel, tip to sample, sample to tip, tunneling current flows. Move the tip 1 angstrom closer, 1/10 of a nanometer, and current increases by a factor of 10. This is the key. This is why atomic resolution works. Scan the tip across the surface using piezoelectric actuators. Measure current. Map the surface atom by atom. Published in Physical Review Letters, July 1982, and verified in thousands of labs since. Apple's Phys, Letting, August 1982. Multiple papers. Immediate recognition. Modern STMs achieve resolution below 1 angstrom, 0.1 nanometers, 10 picometers. That's smaller than a hydrogen atom's diameter. You see individual atoms, chemical bonds, electronic clouds, defects, grain boundaries, adsorbates. Real space imaging, no need for crystallography, no averaging over unit cells, direct observation, 1 atom at a time. Up to 80 frames per second in video rate STMs demonstrated in 2024, published in Progress in Surface Science. April 18th, 2024 on high-speed scanning tunneling microscope techniques. You watch atoms move. Diffusion, adsorption, surface reactions. Oxygen atoms on ruthenium 0001 surface. CO molecules flipping on sodium ion surfaces. Real-time quantum dynamics visible. Adjust tip height via piezo actuators. Z-piezo responds to current changes. Height maps the surface. Atomic resolution. Used when surface is rough or when precise height measurement matters more than speed. Slower than constant height, but more versatile. Works on varied topography. dI over dV versus voltage. This reveals the local density of electronic states at that exact location. You see how electrons fill energy levels, surface chemistry, bonding, band structure, superconducting gap, all visible in the IV curve. Dirac cone in graphene imaged this way. Electronic structure confirmed. Transition metal dichalcogenides, molybdenum disulfide, tungsten diselenide, black phosphorus. The Jarvis STM database published in Scientific Data. February 11th, 2021 contains 716 computed STM images of exfoliable, 2-dimensional materials. Researchers compare experimental images to computational predictions using density functional theory and the Tursoff-Hamann method. Phase identification, defect analysis, lattice distortions. Machine learning models trained on the database achieve high accuracy in identifying Bravais lattice types from STM images. Thin gold layer or image in liquid, electrochemical STM, special tips, platinum iridium, gold, but it works. DNA imaged in 1990, proteins imaged, viruses, enzymes, molecular machines, all visible if you get the technique right. Challenges remain: sample preparation, conductivity, stability, but progress continues. Papers published through 2022 on STM of biological structures, still an active research area. Bruker in Massachusetts, Oxford Instruments in UK, desktop models, lab models. Some operate in air, ambient conditions. Others need ultra-high vacuum, UHV STM. Pressures below 10 to the minus 10 torr, prevents contamination, clean surfaces. Prices start at $50,000 for basic models. Research models cost $500,000. Top systems with full capabilities approach $1 million. Stability is everything. Vibrations ruin atomic resolution, anechoic chambers, dedicated concrete rooms, acoustic isolation, electromagnetic shielding, floating tables, air springs, mechanical springs, gas springs, dampers, eddy current damping. Magnetic levitation in the original 1981 design by Binnig and Rohrer. They used magnets to float the STM, no mechanical contact, no vibration transfer. Electrochemically etched in sodium hydroxide or potassium hydroxide. Current cutoff at the right moment. Creates sharp apex. Platinum iridium for corrosion resistance. 80% platinum, 20% iridium wire. Gold for specific applications. Soft. Forms single atom tips easily. The last atom on the tip does the imaging. One atom's wave function. If multiple atoms stick out, you get blurry images. Multiple tip atoms give double images or ghost features. Contamination is constant. Atoms from the surface adsorb onto the tip. Tips must be cleaned or replaced between scans. Voltage pulses clean tips, high voltage. Brief, desorbs contaminants, or just approach a new area, fresh tip apex. Quantum tunneling makes this possible. Classically, the electron can't cross the vacuum gap. The barrier is 5 electron volts, work function of tungsten. The electron needs that much energy to leave the metal. At 1 nanometer separation, that's impossible thermally. Room temperature thermal energy is 0.025 electron volts, a factor of 200 too small. But the electron's wave function extends into the gap, decays exponentially. At 1 nanometer separation, the wave functions of tip and sample overlap. Overlap means non-zero tunneling probability. Apply voltage, creates bias, occupied states on one side tunnel to empty states on other side. Current flows, science. The tunneling current I depends exponentially on the gap distance d. I equals I0 times e to the negative 2 times kappa times d, where kappa is the decay constant. Kappa equals square root of 2 times mass times work function divided by h bar squared. For typical metals, kappa is about 1 inverse angstrom, so increasing d by 1 angstrom multiplies the current by e to the minus 2, factor of 7.4. Decrease d by 1 angstrom and current multiplies by 7.4. This exponential sensitivity gives atomic resolution. Moving from valley between atoms to directly over an atom changes d by fractions of an angstrom. Current changes by factors of 2 or 3, easily measurable. Spin textures, published in multiple papers through 2024, combines topology and quantum tunneling. Pitchblende, stable on human timescales, 4.5 billion year half-life. But it decays, emits an alpha particle, helium-4 nucleus, 2 protons, 2 neutrons, becomes thorium-234. The thorium decays further. Protactinium, another uranium isotope, radium, radon, polonium, lead, decay chain, 14 steps, ends at lead 206, stable. Measured from emitted particles, the Coulomb barrier around the nucleus is 25 million electron volts, calculated from nuclear radius and charges. Classical physics says trapped forever, energy too low, can't escape. Quantum physics says tunnel, 1928 again, Gamow, Gurney, Condon, same year, same solution. Independent derivations, all reach same conclusion. 2 neutrons, tightly bound. Binding energy per nucleon in helium-4 is 7.1 million electron volts, very stable. The alpha cluster oscillates inside the parent nucleus, bounces around, confined by the nuclear potential well. Strong force attractive inside, Coulomb force repulsive outside, creates a barrier. The alpha hits the barrier, reflects, classical bounce, hits again, 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 trillions of times per second, frequency around 10 to the 21 hertz. Each time there's a probability it tunnels through. Small probability, but non-zero, eventually it escapes. They noticed alpha emitters with higher energy particles have shorter half-lives. Empirical observation, exponential relationship, log of half-life versus inverse square root of alpha energy, straight line, different isotopes, different elements, same relationship. Gamow's theory explained why. Higher energy means the effective barrier width is narrower. The alpha starts from higher energy level. The Coulomb barrier is wider at low energy, narrower at high energy. Because barrier height is energy dependent. Above threshold, the barrier doesn't exist, so higher energy alpha sees narrower barrier. Tunneling probability increases exponentially. Half-life drops exponentially. 8 million electron volt alpha particles, half-life 138.4 days, uranium 238, 4.2 million electron volt alpha particles, half-life 4.468 billion years. Factor of 2 in alpha energy, factor of 10 to the 10th in half-life, 10 billion, exponential. Tunneling math, Gamow-Sommerfeld factor explains it. Penetration probability through Coulomb barrier. Solve the Schrödinger equation for the potential. WKB approximation, Wenzel-Kramer's Brillouin method. Good approximation for slowly varying potentials. Alpha decay fits perfectly. The barrier stays intact. The wave function extends through. Probability amplitude on both sides. Square it. Get detection probability. The particle appears outside. As Gurney and Condon wrote in 1928, it has hitherto been necessary to postulate some special arbitrary instability of the nucleus, but the alpha particle almost slips away unnoticed. Quantum tunneling, no violence, no explosion. Just probability and time. Alpha decay releases energy, thermodynamically favored, but kinetically blocked by the barrier. Tunneling allows it. Thorium-232, 14 billion year half-life. Radium-226, 1600 year half-life. Radon-222, 3.8 day half-life. Plutonium-238, 87.7 year half-life. All quantum tunneling, all exponentially sensitive to alpha energy. Smoke detectors use americium-241, alpha emitter, 5.49 million electron volt particles, 432.2 year half-life. The alpha particles ionize air in a small chamber, creates current. Smoke particles disrupt the current. Alarm sounds. Tunneling keeps your house safe. Millions of detectors, all tunneling alpha sources, regulated, safe, low activity, microcuries. Plutonium-238, alpha decay, 5.5 million electron volts per decay. Heat from kinetic energy of alphas convert to electricity using thermocouples. Seebeck effect. Temperature difference generates voltage. Voyager 1 and 2, launched 1977, still operating. 47 years. In 2024, Cassini, New Horizons, Curiosity rover, Perseverance rover, all powered by tunneling alpha particles. No solar panels needed. Deep space. Low light. RTGs work everywhere. As long as plutonium decays, and it will for centuries. Tunneling guarantees it. Underground uranium and thorium deposits emit alpha particles for billions of years. Geologic time. The particles slow down in rock, grab electrons from surrounding atoms, become neutral helium gas trapped in rock formations. Natural gas contains helium, extracted during processing, separated cryogenically. 99% of Earth's helium is from alpha tunneling. Without quantum mechanics, no party balloons. More importantly, no MRI machines. No superconducting magnets, no cryogenics, no helium neon lasers. Industrial applications everywhere, all from radioactive decay, all from quantum tunneling. The lifetime sensitivity to particle energy proves it. Change energy by 10%. Change lifetime by a factor of 1,000 or more. No classical theory does that. Only exponential tunneling probability. Temperature dependence is weak. Unlike chemical reactions, alpha decay rate barely changes with temperature because tunneling doesn't need thermal activation. It's purely quantum. Wave function penetration, measurement collapses the wave. Alpha detected outside. Nucleus transmuted, irreversible. Slower than alpha decay typically, but same principle. Quantum probability of barrier penetration. Klinman at University of California, Berkeley publishes evidence of quantum tunneling in enzyme reactions. Hydrogen transfer, carbon-hydrogen bond cleavage, proton tunneling. The enzyme doesn't just lower the activation energy, it promotes tunneling. Published in Science, March 10, 1989. Kinetic isotope effects, temperature dependence. Data doesn't match classical transition state theory. Proton abstraction step. Published in Proceedings of the National Academy of Sciences, December 8, 2009 by Dan T. Major, Jolly Gao, and others. The enzyme catalyzes proton transfer from nitroethane substrate to aspartate, 402 residue in the active site. Researchers measure kinetic isotope effects, hydrogen versus deuterium, hydrogen versus tritium. The ratios don't match classical predictions. Path integral free energy perturbation method used, PIFEP, includes quantum nuclear effects, 0-point energy, tunneling. KH over KD equals 9.2 in the enzyme active site, 7.8 in pure water without enzyme. Looks small, but significant. Means enzyme enhances quantum effects, Swain-Schad. Exponent calculated. Relates HT isotope effect to DT isotope effect, 4.3 in enzyme, 3.5 in water. Classical semi-classical limit is 3.3. Above 3.3 indicates tunneling. Both show tunneling, but enzyme shows more. Path integral simulations confirm it. The tunneling probability is higher in the enzyme active site than in bulk solution. Why? The enzyme positions reactants precisely, compresses the donor-acceptor distance, reduces the effective barrier width. Tunneling probability increases exponentially with decreasing width. The enzyme evolved, or at least tolerates this geometry. Active site architecture, hydrogen bonding networks, electrostatic pre-organization, all contribute. The enzyme doesn't just stabilize the transition state, it optimizes the tunneling coordinate. Hydrogen atom with 2 electrons, H-, moves from substrate ethanol to NAD plus cofactor, becomes acetaldehyde and NADH, essential metabolism. Temperature dependence of kinetic isotope effects shows non-classical behavior. Isotope effect increases as temperature drops. That's tunneling signature. Classical reactions show the opposite trend. Higher temperature means bigger isotope effect classically, because more molecules have energy to cross barrier. But tunneling is temperature independent or weakly dependent, so lower temperature gives higher relative tunneling contribution. KIE increases, exactly what's observed. Studied by Judith Klinman and Michael Knapp. Published in Journal of the American Chemical Society, 2002. Temperature-dependent isotope effects. Enormous primary KIE, KH over KD up to 80 at low temperature. Room temperature KIE around 30. Classical limit is about 7 for CH bonds. Factor of 4 to 10 above classical. Tunneling dominates, coupled to protein dynamics. The enzyme structure fluctuates. Conformational sampling. Brings donor and acceptor close. Tunneling window opens. Donor acceptor distance drops below 3 angstroms. Reaction happens. Tunneling. Structure relaxes. Donor acceptor distance increases. No tunneling window, no reaction. Gating. Conformational gating of tunneling. Dynamics matter. Glycolysis, Krebs cycle, central metabolism. Deuterium substitution slows the reaction by a factor of 3 to 7 depending on conditions, more than classical predictions. Quantum effects proven. Temperature dependence analyzed. Marcus-like theory applied. Environmental reorganization controls tunneling probability, not just the hydrogen transfer coordinate. The entire active site participates. Essential for DNA synthesis. Folate metabolism, tetrahydrofolate production, cancer drug target. Methotrexate inhibits it, mimics dihydrofolate, binds tightly. Blocks active site. Stops DNA synthesis, kills rapidly dividing cells. Quantum tunneling contributes to DHFR mechanism. Published work through 2010. QM-MM calculations. Quantum mechanics, molecular mechanics. Treat active site quantum mechanically. Treat rest of protein classically. Hybrid method. Tunneling corrects the reaction rate by factors of 10 to 100 compared to purely classical calculations. Not dominant, but significant. Estimate from Klinman based on systematic studies across enzyme families published through 2020. Comprehensive review. Not all enzymes tunnel significantly. Many rely purely on classical barrier lowering. Transition state stabilization. Electrostatic catalysis. Ground state destabilization. All classical mechanisms. But for fast hydrogen transfer, tunneling helps. Light particle. Proton mass, 1836 times electron mass. Small. High tunneling probability. Nature uses it. Precise positioning of active site residues, hydrogen bond networks, dynamics coupling, all could be evolutionary optimization for quantum effects or coincidence. Tunneling happens automatically when barriers are thin and particles are light. Enzyme may just position things close. Tunneling emerges. No specific evolution needed. Debate continues. Research ongoing. No direct observation possible. You measure isotope effects, primary KIEs, secondary KIEs, temperature dependence, pressure dependence, Swain-Schott exponents, all diagnostic tools. Deviations from classical predictions indicate tunneling. Deviation magnitude quantifies tunneling contribution. The data says it's real, multiple enzyme families, consistent results, different research groups, independent confirmation, physics, working inside biology. Quantum biology is broader than enzymes. Photosynthesis uses quantum coherence, energy transfer in light harvesting complexes, excitant transport, quantum beating. Avian magnetoreception possibly uses radical pair mechanism, quantum entanglement, spin states, bird navigation, DNA mutation through proton tunneling in base pairs, tautomerization, hydrogen bond rearrangement, point mutations, evolution. Olfaction might use quantum tunneling, vibrational theory of smell. Electrons tunnel based on molecular vibrations. Controversial, but possible. Life uses quantum mechanics everywhere you look. Enzymes are just one example. If you value documented physics and biology like this, subscribe. It's the best way to support our work. Let's continue. Leo Esaki invents the tunnel diode in 1957 at Tokyo's Sushin Kogyo. Company later renamed Sony in 1958. He makes a heavily doped PN junction, doping concentration above 10 to the 19th atoms per cubic centimeter. Both sides, N-type and P-type. Phosphorus doping on N side, boron doping on P side. Very high. Depletion region shrinks to 10 nanometers or less. Electrons can tunnel through. Quantum mechanical transmission through thin barrier. Works at room temperature. No cooling needed. Electrons tunnel from filled states to empty states. Current increases with voltage. Normal diode behavior, but at much lower voltage. No more overlap. Electrons can't tunnel to valence band. Current decreases, negative resistance. Current decreases as voltage increases, 0.1 volts to 0.5 volts typically. This is impossible classically. Ohm's law says current increases with voltage. Not here. Quantum tunneling enables it. 20 to 1 in excellent diodes. The negative resistance region enables oscillators. Apply DC voltage in negative resistance region. Circuit oscillates. AC output, frequency determined by circuit inductance and capacitance. Microwave frequencies achievable. Gigahertz, terahertz possible with proper design. Low-noise amplifiers for radio astronomy, satellite communications. The negative resistance compensates transmission line losses, extends range, boosts weak signals, still used in niche applications. Less common now than in 1960s and 70s. Transistors improved, replaced many tunnel diode applications. But tunnel diode remains fastest diode, terahertz switching. Quantum tunneling is inherently fast, femtosecond timescales. Esaki published his results in Physical Review in 1958. Immediate recognition. New physical principle and practical device. He shared the 1973 Nobel Prize in Physics with Ivar Giæver and Brian Josephson. All three worked on tunneling in different contexts as graduate students or young researchers. All three made fundamental discoveries. Tunneling connects them. Gate voltage controls tunneling through a barrier, band-to-band tunneling, valence band to conduction band, lower voltage operation than conventional MOSFETs. 0.2 volts gate voltage versus 1 volt for standard transistors in 2024. Power consumption drops by a factor of 100 potentially. Published in IEEE Electron Device Letters and IEEE Transactions. On electron devices through 2024, scaling up to VLSI chips is the challenge. Millions of transistors, billions. Process variations. Tunneling is exponentially sensitive. Small thickness changes cause large current variations. Manufacturing tolerance becomes critical. Research continues. Low-power chips need TFETs, mobile devices, Internet of Things, battery life, heat dissipation. All benefit. Different physics, but also quantum tunneling. Brian Josephson predicted in 1962 as a graduate student at Cambridge, 22 years old. Two superconductors separated by thin insulator, 1 nanometer thick, Cooper pairs tunnel through. No voltage applied, yet current flows, DC Josephson effect, supercurrent, zero resistance, dissipationless, where E is electron charge and H is Planck's constant. Voltage to frequency conversion, fundamental physics relation. Used to define the volt now, Josephson voltage standard, NIST, metrology institutes worldwide. Voltage references based on Josephson junctions, count photons, measure frequency, calculate voltage. Exact. Quantum mechanics defines the standard. Quantum interference of supercurrent, most sensitive magnetometers ever built, detect magnetic fields of 10 to the minus 15 Tesla. Femtotesla, that's 1 billion times weaker than Earth's magnetic field, 1 trillion times weaker. Brain activity produces magnetic fields around 10 to the minus 13 Tesla. 100 femtotesla, squids can map it. Magnetoencephalography, MEG, brain imaging without electrodes. Quantum computing, IBM, Google, Rigetti. IonQ uses ion traps, but most solid-state qubits are superconducting. Transmon qubits, flux qubits, phase qubits, all use Josephson junctions. Tunneling controls the quantum state. Energy levels set by junction parameters, capacitance, Josephson energy, charge, and flux quantum numbers, superposition, entanglement, quantum gates, all require control of tunneling through Josephson junctions. The 2025 Nobel Prize in Physics went to John Clark, Michel Devore, and John Martinis, published October 7, 2025, by the Royal Swedish Academy of Sciences. They demonstrated macroscopic quantum tunneling in superconducting circuits. University of California, Berkeley, Yale, Google, hand-sized electrical circuits behaving like single quantum particles. Cooper pairs, tunneling. Billions of electrons moving collectively. Quantum superposition at macroscopic scale, tilted washboard potential analogy. The system's electrical phase behaves like a particle trapped in wells separated by barriers, energy quantized. Transitions via tunneling, not continuous, discrete jumps, measured, confirmed. Quantum mechanics isn't microscopic anymore, it scales. Pyramid shape, nitrogen at apex. 3 hydrogens at base, but the nitrogen can flip, pass through the plane of the hydrogens, become inverted pyramid, then flip back. This is quantum tunneling through a potential barrier. The molecule oscillates between 2 configurations. 2100 Kelvin equivalent temperature. Thermal energy at room temperature is 0.026 electron volts. Factor of 80,000 too small. Nitrogen stays on one side. Pyramid locked. Molecule has permanent dipole. 1 configuration. 23.7 billion inversions per second. Each molecule flips back and forth constantly. Both configurations superposed. Published in molecular spectroscopy texts and verified in gas phase microwave absorption experiments since the 1930s. Harold Clayton and Neil Williams first observed inversion spectrum in 1934. Microwave spectroscopy. Ammonia was the test molecule. Inversion splitting clear. Charles Towns and colleagues at Columbia University. James Gordon, Herbert Zeiger, first maser. Microwave amplification by stimulated emission of radiation. They separate ammonia molecules by inversion state, use electric field gradient. Inhomogeneous field. Stark effect. Molecules in different inversion states deflect differently. Select upper state. Feed into resonant cavity. Stimulated emission at 23.7 gigahertz. Coherent microwaves. Amplification. The predecessor to the laser. Arthur Schawlow and Towns proposed optical maser in 1958. Theodore Maiman built first laser in 1960. Ruby laser. 694 nanometers. All from ammonia inversion. All from quantum tunneling. Energy splitting equals twice the tunneling matrix element. Inversion frequency directly measures tunneling rate. Change the isotope, use deuterium instead of hydrogen, and the frequency drops. ND3, nitrogen deuteride. Inversion frequency 1.6 gigahertz, factor of 15, slower than NH3. Heavier mass, lower tunneling probability. Exponential dependence on mass. Square root appears in the tunneling exponent. Double the mass, square root of 2. Exponent increases, probability decreases, exactly as predicted. Quantum mechanics tested and confirmed. Hydrogen moves between two oxygens. Tunneling splitting, spectroscopy measures it. Methyl group rotation in toluene. CH3 internal rotation, threefold barrier. 3 equivalent wells, tunneling between them. Splits, rotational levels. Microwave spectroscopy resolves it. Melanaldehyde. Proton transfer in intramolecular hydrogen bond. Heavy light heavy mass asymmetry, ideal for tunneling. Large deuterium isotope effect, factor of 10 or more, studied extensively. Any situation with a double well potential and light particles shows molecular tunneling. Quantum mechanics dominates, mass in denominator of tunneling exponent. Light particles tunnel easily, heavy particles tunnel slowly. This is why electron tunneling is so common. Electron mass 9.1 times 10 to the minus 31 kilograms. Proton mass 1.67 times 10 to the minus 27 kilograms. Factor of 1800 heavier. Tunneling probability drops exponentially, but still happens. Protons light enough on molecular scales. Tunneling measured. Terahertz spectroscopy. Hydrogen bonded systems everywhere show tunneling. Ice, liquid water, DNA, proteins, membranes. Quantum effects in hydrogen bonds contribute to structure and function. Proton tunneling and hydrogen bonds reviewed in Royal Society Philosophical Transactions, published June 6, 2018. Comprehensive analysis, applications to enzyme catalysis, materials properties, atmospheric chemistry. Interstellar chemistry relies on tunneling, cold molecular clouds, 10 to 20 Kelvin, no thermal energy. Classical reactions stop, but quantum tunneling continues. Hydrogen atom tunneling, deuterium tunneling, forms molecules on grain surfaces. Water, methanol, formaldehyde, organic molecules. Without tunneling, no chemistry at low temperature, no star formation. Clouds don't collapse properly, no planet formation, no prebiotic chemistry. Tunneling enables cold chemistry. Space is cold. Tunneling keeps it active. All wave function penetration through classically forbidden barriers. All probability and detection. Solve for a potential barrier. A wave function doesn't vanish inside. Exponential decay. Non-zero amplitude beyond. Square gives probability. Integrate gives transmission. Tunneling. Mathematics predicts it. Experiments confirm it. Technology uses it. 80 years from Gamow's first paper to the 2025 Nobel Prize. Continuous thread. Quantum tunneling discovered, explained, applied, extended. Macroscopic scales. Technological scales. Biological scales. Astronomical scales. Every scale. One phenomenon. Wave nature of matter. Heisenberg uncertainty. Superposition. Measurement. Collapse. Detection. The full quantum mechanical picture. Tunneling in all. Quantum sensors, squids, atomic clocks, gravitational wave detectors, all rely on quantum effects. Tunneling is one. Nanoscale electronics, transistors shrink, 1 nanometer gates, 2 nanometer process nodes. Tunneling leakage becomes dominant, must be managed, or used. TFETs turn leakage into feature, control it, engineer it. Molecular electronics, single molecule transistors, single atom transistors. Tunneling is the mechanism. No other transport works at that scale. Waves extend, overlap, interfere. Exist everywhere probability is non-zero. Measure and collapse. But before measurement, everywhere. That's quantum mechanics. That's tunneling. That's reality. Your phone wouldn't work. Microscopes couldn't see atoms. Radioactivity wouldn't happen at measured rates. Enzymes would be slower. Electronics would use more power. Molecules couldn't invert. The universe would be different, but it's not. Tunneling is real. Math proves it, experiments show it, technology depends on it, life exists because of it. Energy appearing where it shouldn't, probability becoming detection, math becoming observable, physics becoming technology. That's the story. 7 ways, 7 windows, one phenomenon. Quantum tunneling everywhere.